Are you looking to strengthen your knowledge in bioprocess engineering? Whether you're a student, researcher, or industry professional, Bioprocess Engineering Online offers a series of free, expert-led video tutorials. Explore our growing library of tutorials that cover the core principles and real-world applications of bioprocess engineering, including enzymatic bioconversions, microbial fermentations, animal cell culture processes. The Bioprocess Engineering Online Tutorials library is organized into 4 sections: Bioprocess Engineering Scope and Methodology, Microbial Fermentation Processes, Animal Cell Cultures Processes, and Bioprocess Economic and Environmental Evaluation. The first section of the library introduces the scope and methodologies of bioprocess engineering. It is primarily intended for newcomers to the field. The tutorial on industrial bioprocesses reviews the main types of bioprocesses using enzymes, microorganisms, and plant or animal cells. Their wide range of applications across industries, from pharmaceuticals to food and other bio-based products, and the key upstream and downstream unit operations involved. In the tutorial Bioprocess Design and Scale-Up, you will learn the key challenges of scaling up bioprocesses from laboratory to industrial scale, how to tailor bioreactor design and operating conditions to the specific requirements of enzymatic or cellular biocatalysts, the main engineering tasks involved in process design, including material balances, energy analysis, and equipment sizing. In the tutorial Bioprocess Simulation Models, you will explore the key role of simulation in bioprocess development, particularly for digital scale-up and process optimization, how knowledge-driven models are built on a fundamental understanding of underlying phenomena, how model equations are derived from the integration of material balances, thermodynamic principles, and kinetic laws. The tutorial Bioprocess Engineering Toolbox presents the 3-stage framework of concepts, methods, and knowledge used in bioprocess engineering education. The first stage covers scientific fundamentals, providing essential understanding of biological and physicochemical phenomena. The second stage focuses on the modeling and design of individual unit operations. The third stage addresses the integrated optimization of the overall bioprocess. The second section of the tutorial library focuses on microbial fermentation processes, including their modeling, scale-up, and optimal operation. In the tutorial Microbial Fermentations Governing Phenomena, you will learn that aerobic fermentation kinetics are governed by 3 key types of phenomena. First, microbial reactions, which describe how cells grow and convert substrates into products through their metabolism. Second, mass transfer, which ensures the efficient supply of essential components, such as nutrients and oxygen, particularly critical in aerobic processes. Finally, fluid flow, including mixing and agitation in the bioreactor, which determines system homogeneity, while also generating shear stress that can impact cell viability. The tutorial Microbial Cell Kinetics reviews the laws governing microbial activity in fermenters. First, growth rate laws describe how cell populations increase under varying conditions, particularly as a function of nutrient availability. Next, rate expressions model how substrates are consumed and how metabolites or products are formed during the process. Finally, physiological state models account for the fact that cells do not remain constant. They adapt and can shift their metabolism in response to environmental conditions. In the tutorial Oxygen Transfer and Consumption in Microbial Fermentation, you will learn about the critical role of oxygen in aerobic fermentation kinetics. On one side, oxygen consumption, which depends on the metabolic activity of the cells. On the other side, oxygen transfer from the gas phase into the liquid medium, governed by oxygen solubility and gas-liquid transfer efficiency. A key condition throughout the process is maintaining a balance between oxygen transfer and oxygen consumption to ensure optimal microbial activity. In the tutorial Microbial Fermentation Simulation Models, You will learn how to construct knowledge-driven models based on fundamental principles such as mass balances, thermodynamics, and kinetics. The first step is to define appropriate rate laws, describing microbial reactions, as well as key phenomena like oxygen transfer. These elements are then combined into mathematical equations, which are integrated over time to simulate the dynamic behavior of the fermentation process. In the tutorial scale-up of microbial fermentation aeration, you will explore the challenges of aeration during scale-up as oxygen transfer becomes more difficult with increasing reactor size. A key aspect is the scaling of gas flow, including volumetric airflow rate and superficial gas velocity, to maintain sufficient oxygen supply. At the same time, agitation power must be carefully adjusted, as it directly influences mixing and oxygen transfer efficiency, typically characterized by the volumetric mass transfer coefficient, KLA. The tutorial Microbial Fermentation Optimization Criteria presents the three key metrics used to evaluate and optimize fermentation processes. First, productivity, which measures the amount of product generated per unit volume and time. Second, the substrate-to-product conversion yield, which reflects how efficiently the substrate is converted into the desired product. Finally, production cost per kilogram of product, which depends largely on both productivity and conversion yield. In the tutorial Continuous Microbial Fermentations, we explore the fundamental principles, kinetic behavior, and optimization strategies of continuous processes. Continuous fermentations can be operated over extended periods under substrate-limited conditions while maintaining steady-state concentrations. A key aspect is the optimization of operating parameters, particularly the dilution rate and the feed substrate concentration. In practice, these systems are often limited by oxygen transfer capacity, which sets an upper limit on the achievable biomass concentration. In the tutorial Fed-Batch Microbial Fermentations, you will learn the fundamental principles, kinetic behavior, and optimization strategies of fed-batch processes. Fed-batch fermentation is based on the controlled addition of substrate, allowing the maintenance of low and nearly constant substrate concentrations. A key challenge is to optimize the feeding strategy, particularly the feed rate and substrate concentration, to maximize productivity. However, as in other aerobic processes, performance is often limited by oxygen transfer, which ultimately constrains the maximum achievable biomass. The third section of the tutorial library focuses on the specific features of animal cell culture processes, which share many common principles with microbial fermentations. In the tutorial What Governs Animal Cell Cultures in Bioreactors, you will learn that cell culture kinetics are driven by three key types of phenomena. First, cellular kinetics, which includes cell growth, cell death, and metabolic activity. Second, mass transfer, particularly oxygen supply and carbon dioxide removal, both essential for maintaining cell viability. Finally, fluid flow, including mixing and agitation, where shear stress must be carefully controlled due to the fragility of animal cells. The tutorial Animal Cell Kinetics in Bioreactors reviews the laws governing cell behavior in culture systems. First, growth and death rate laws describe how cell populations evolve under varying conditions, particularly as a function of nutrient and metabolite concentrations. Next, production kinetics account for the formation of metabolites and recombinant proteins. Finally, nutrient consumption kinetics describe the uptake of key substrates such as glucose, oxygen, and amino acids. The fourth section of the tutorial library focuses on the economic and environmental evaluations of bioprocesses. In the tutorial Bioprocess Economic Evaluation, you will learn how to assess the cost of bioprocesses. First, capital investment, which includes the cost of equipment and infrastructure, and is largely determined by process scale and equipment size. Second, production costs, which encompass operating expenses such as raw materials, energy, equipment use, and labor. Finally, cost benchmarks, which provide typical cost ranges for bioprocesses and help evaluate economic feasibility and competitiveness. In the tutorial lifecycle assessment of bioprocesses, you will learn how to apply LCA methodology to evaluate environmental impacts across the entire lifecycle of a bioprocess. The approach is based on a detailed inventory of material and energy flows associated with the process. From this inventory, key environmental indicators are calculated, such as primary energy consumption, water use, and global warming potential. The tutorial LCA guided bioprocess environmental optimization illustrates how life cycle assessment can be used as a powerful tool to improve the environmental performance of bioprocesses. Based on LCA results, the main sources of environmental impact can be identified, enabling the development of targeted reduction strategies. This includes minimizing key indicators, such as energy consumption, water use, and emissions. Practical solutions often focus on improving resource efficiency, for example through water recycling and heat integration. All the tutorials are available on our Bioprocess Engineering Online YouTube channel and on our website, bioprocessengineeringonline.com.